Okay. Before we start, you have any questions or concern? All right. If not, then let's start. We talk about the differentiability. Um, let's just start with the one variables. Let's move to our notes. What does it mean to be differentiable? Okay. Uh, X is one variable. Uh, okay. You recall that the derivative is defined by this one here. What you call, say, x going to f of x, say at a point, say a, if limit exists, then we say this is differentiability. F is differentiable x cos a. Okay. So now the last time I mentioned that the if you replace h by a factor, is that not good is one. What happens to this one? Right. Cannot be generalized to two variables. So A here is a factor. A is a factor. Problem. There's A, uh, what's it called? Division by a factor is not defined. You cannot define number by factor. This is basically, it is number defined by a factor. Okay, so somehow we have to modify the equation first. Okay, so you need to the definitions. Okay. So the question is how we define this, how would we modify uh, the the definitions. Okay, so let's modify this. All right. So what does it mean by this is one variable again? So we try to avoid. So in one variable, this would be here. Um, say a plus 8. Okay, so this is. So first, let's remove the limit. Well, if you remove the limit, then we get something like this. Then we won't have this a equal again because we just have this approximately. And this is correct if h is small. The get problem with the notes. If h is small. Okay, so meaning of the limit h goes to 0 is equal this one. So the limit, meaning if h is small, then this would be approximately same. So left hand side the same. All right, so then if the left hand side is almost equal to the right hand side, then we should have that uh, remove the h by multiplying by h because h is now non-zero. Equals to h times, okay. And let's remove a to the right hand side. So we get something like this. Of a not equal plus h times. Okay. And let's put the equal sign back. But if you put the equal sign back, then we won't have the, okay, and put, meaning that if you like to have the equal sign, then we should put the difference. That's some error. Okay, and the small should be the error should be small. Okay, that means all right. And if you recall, this is actually the equation of y equals mx plus. Oh, I should write down something like this. Equation for tangent line. Okay. So these equations can be interpreted as a approximations of this value by tangent line at this point. Mm, This is the picture, should look like this one. Tangent line. A. So the values near A, so not too far from A. Uh, so this is the value, say this is f of A, sorry, f of A plus H. So this is A plus H is approximated by this value. That is f of A plus. Okay, so this. So what is the error? The error is this one. There's the error. Okay. And the error is something like the should satisfy this one here. The error defines, sorry, if you compare it to H, it's even much smaller. Okay, so that means the error is much smaller than H. Okay, so this is the meaning of a differentiability in term of uh, a approximations by tangent line. Okay, so now we can redefine f is differentiable at x equals a if this is the name f can near a say something like this. Value of f of the functions near x to a can be approximated by tangent line or we can say linearly by linear equations at x equals a with error, say, small error. What does it mean, small error? Small error means that error divided by h. Okay, so this is the error should be even much smaller than h. Okay, so this is how we redefine the what we call a differentiability. Okay, let me just close this OneNote. Get the problem with this. I have to reset this OneNote. Let's see. All right. Okay. So then let's do some examples. Okay. Um, Example. Uh, what kind of function you know that is not differentiable? The easiest one. What should be the easiest example of non-differentiable? F not the non-differentiable at a point, say 0. What's the function looks like? Or what kind of function is that? Anyone? Hello? Anyone out there?
Yes, sir.
Uh-huh. What kind of function do you know is not differentiable? The easiest example of non-differentiable.
Is y equals to absolute value x of x not differentiable, sir?
Yes, that's the one that the easiest one. We know that this is not differentiable at x equals 0. This is the picture. Okay, because the limit, uh, by definition of using the limit, right? So let's uh, check by using this new definitions. Okay, definitions. Okay, here. So if we would like uh, to approximate these functions using any y equal mx plus b. Okay. Uh, so suppose uh, near 0 is approximated by uh, this is okay. So what's wrong? Not what's wrong. What happened here? Okay, so let's compute the difference. Okay. So h here. So let's compute the difference. compute H, the difference with the X plus P, if you did that H. Okay, so this you get something that this is absolute value of say H is positive. So absolute value is just H. Okay, and then minus you plug in H to mx plus p. So oh, sorry, there should be no v at all. Okay, so that's a linear equations. So this gives you just h1 minus m. Okay, let's see here. Let's now compute the what is the error? All right. So this is the error. Okay. And let's compare this to H. The ratio. If we compute error over the H, let's see. Let's just all right. And if unless m is equals to 1, this is not for sure this is not going to 0 for H. Okay. Unless m is equal to 1. Okay. But what happens if m equals 1? When when m equals to 1, so consider the H negative. Okay, because when H negative, what we have is that error over the H. Again, look at the picture. M is 1 is this one. Okay, so this would be the error. Okay, so now the error is actually large here. So this is error is just okay. So the value is this is just negative H, right? So uh, the error should be negative 8, right? Because this is 8, this is H, and this is letter H. This value. So you get sure it's not to 0 either when H goes to 0. Okay, so the conclusion is that here in this equation, in this problem, the error is not much smaller than H. Therefore, not differentiable. Okay. Okay. So that's the reason why this picture is not differentiable. This is not differentiable. f equals 0. Why? Because the error with any error is not going to 0. Sorry, over 8. These are not differentiable. All right. Okay, but the good thing about the this definition is that because now you don't have any deficiencies in this definitions. Okay, so this is something that we can adapt for two variables. All right. So there's no deficiencies involved in, uh, in the definitions. We can adapt uh, for two variables. Okay, so how we adapt this? Well, we can say that uh, so if we say something like this, we will do the detail. Um, f, with two variables, f is differentiable. Uh, f, now the point is that uh, 0, this is a vector. Okay. If the value of fx near 0 can be approximated by, because the earlier we have a tangent line, we have now tangent, not only a line but a plane, tangent plane with a good error. But that's really a good error. Meaning that the error compared to the difference between x and uh, here vector, this goes to 0 or h goes to 0. So this is actually limit of two variables, or you can. Okay, so the thing is how we can find out a tangent plane. Okay, all right, any questions up to now? All right, so let's show you the picture. Okay, now I didn't graph it on Maple. You can use Maple, whatever you to check this one, plot this one, -10 square root of absolute value of xy. Okay, so this is the picture here. Okay, so this value is 0 along the x-axis, y-axis. Okay, and you have negative because xy and take absolute value, right? So that's non-negative. Okay, and then you take square root. Okay, that's all right. And multiply by a negative tens, make it a negative. Okay, so actually negative, except at uh, x-axis and y-axis here. There, here. Okay. So if you look at the uh, what do we call it? Level curves. Okay, so this level curves, this is the picture. Okay. So then what should be the plane that approximates this value right here? The plane should be, this is constant. So this is z equal 0. Okay. So what's the error? Well, the error should be this one here. At this point, for example, is 0. This is 8. Compared to this one here. For example, here, that's the value at each factor. Okay. So then that is the error. Okay. And that is even larger than the age. So this is not differentiable. Okay. Just okay. So this we have earlier. Okay. So this is I won't write it down. Oh, we define what we call linear, locally linear. Okay. F is locally linear if f can be written as this one, f of b times this one times this with something here. Okay, and there's a note here. This one is goes to 0, goes to 0. Okay, so this part goes to 0. And if you multiply another by h, because h is small, that's even smaller. Okay. And this is this epsilon 2 is small, goes to 0. And if you multiply by h, it's getting even smaller. Okay, so this goes. Okay, so that's saying that the whole thing divided by h goes to 0. It's much smaller than the. Okay, so then that's what we call the locally linear. But what is this? This is the uh, partial derivative. This is partial derivative. Okay. And the thing here is that let me just put this down. Okay, what's wrong with this? Why I have two notes? data f is locally linear if x is now is a vector is okay plus let's see let me just rewrite this. We'll make a copy of the definitions instead of instead of uh, rewriting this. Okay, let me stop the share first. Uh, Something wrong with my notes. Need to reset my laptop. Hold on. Uh,